I'm going to start to introducing our today's speaker. Our today's speaker is Dr. Raul Rincon. He's a postdoctoral associate in the Department of Civil and Environmental Engineering at Rice University. He obtained his bachelor's and master's degree from Universidad de los Andes, Colombia, and his PhD in civil engineering from Rice University. Dr. Rincon's research focuses on modeling infrastructure systems operating under progressive and shock-based hazard, particularly on methods and mechanisms to facilitate adaptive resilience and equitable performance. He's interested in developing multi-scale and probabilistic models that reflect the dynamic interaction between infrastructure systems, societies, and the environment. He received the Best Student Paper Award at the ICOSAR conference on 2025, first place in the Objective Resilience Student competition at the EMI conference 2024, and the Fulbright Scholarship 2019. Dr. Rincon also will join CU Boulder as an assistant professor in 2026. So I think this is a good opportunity for the students who want to reach out to him to learn more about his work. Today, Dr. Rincon will present on examining infrastructure failures in socio-physical system using attributed graph models. By this brief introduction, Dr. Rincon, the floor is yours.
Thank you so much, Farisa. And thank you everyone for joining today and hear this a little bit long presentation. I'll make it shorter, although I saw that I have only 35 minutes instead of 40. I was planning for 40. So let me first share my screen. And let's start with the presentation. Okay. I'm gonna hide this floating panel. Oops. Okay. So thank you again. I'm very happy to be here. It was a nice invitation from the GSC. I had a travel, I moved the travel, so I wanted to be here today. I think it's a good opportunity to share my work that I made or did during my PhD, and also that I'm exploring during my postdoc time. But definitely, this is something I will continue as a future faculty at CU Boulder. So the work that you're going to see today focuses on examining the failure of infrastructure systems, typically evaluated at the network scale. I will make sure to explain this in detail. So let's start by describing the problems that we in this community focus on, NHERI, the NHERI facilities and the NHERI cyber infrastructure. All of the community works in natural hazards. And so natural hazards are one of the stressors of our infrastructure system functionality. Also, progressive stressors can or will or should be taken into account. So the difference is that the natural hazards typically are like shock-based stressors that come in a certain or specific time and largely deteriorate suddenly the functionality of the performance of these infrastructure systems, while progressive stressors will deteriorate the capacity slowly, but the compounded effect can be quite large. And we have to understand as engineers how we can diminish such an impact. So not only the direct impact, which is very important, but also the indirect impact, which it's related to resilience. So as engineers, what we do typically is to model this problem by dividing and conquering. What we do is we divide this problem into expertises. So some people work in defining what is the exposed assets, others work in hazards, others defining what are the consequences or first the damages on infrastructure systems. And then we start combining all together to then bring this damage assessment towards something that is more complicated in terms that it has more uncertainty, such as the recovery process and the resilience estimation. And what we do is we do typically this type of analysis at different scales. So we can start and do a resilience estimation of a specific structure, here a breach, or we can start modeling the combined effect when we consider a portfolio. Now we have thousands of components, but today we're going to focus on the network level when we now have to consider the interaction and the complex emerging properties of the system when now you consider that the functionality of some of the components depend on others. So to link this with the social impact, which is part of the main focus of this presentation, what we typically do is we combine all this together. We have a multi-scale model that is an integrated in the end. And we have to start defining the stressors with complex physical system, the performance. But in the end, you will have something like you observe here, a map with damages where you can place and say, okay, here in these areas we have some let's say some exacerbated damages from the physical perspective. But we want to do it at the social system level. So typically, in our field, we combine these two input and we say, okay, if we have high impact in this area and this is a social vulnerable population, so we try or tend to focus on that. That is the most common approach. So I would say this is based on the proximity of users to the most vulnerable assets. There is something else that we should start checking because we as engineers created these models. We have an abstraction of the problem and we believe in this problem in a certain way, but there are other ways of observing the problem. We may find that our models have some level of uncertainty. Also, we have uncertainty in the type of data, uncertainty in the amount of data per type of social vulnerability. So we could start thinking also in something that goes beyond the social equity modeling to something that I'm calling, and with Jamie, we have been calling equitable infrastructure resilience modeling, which means is trying to focus or placing attention on those areas where our model is telling us like, hey, look, this is a social vulnerable population, but they're fine. They don't have a high impact. However, our model in those areas present a high uncertainty. So these topics that I'm showing you here are going to guide our presentation. So first, I'm going to discuss for those that don't work in modeling, computational modeling, and for those that don't work in network, which is a specific area, I will make a brief introduction on how this is done. Then we're going to jump to the attributed graph models, which is the main focus, how we propose to use them to represent joint socio-physical systems. And we're going to present two additional topics. One, now that we have this way of representing the system, we can evaluate the influence of model fidelity and how we can make it a reduction in computational costs. So let's start with the first one. For those that don't have experience with network modeling, a network typically is a graph, is represented by a graph that is comprised by a set of nodes V and a set of edges E. And that is presented here. Nodes are the circles, edges are the links, and the connectivity that they have will create this type of topological structure. I want to emphasize that from the network science perspective, typically nodes and edges may represent many different things. Relational networks could be, for example, social networks, where the physical location doesn't matter. But for us that we work in risk, it matters because those are specific elements that are exposed to a specific level of a hazard. So we have to keep track of that. Okay, what we could do at this point, just by knowing the topology of the structure, we could start investigating what are the most important elements or components of this infrastructure system to, let's say, prioritize when we want to intervene and make it better for some societies that live there. What you could do is, for example, a ranking-based metric that you have here, degree, betweenness, closeness. Each one focuses on something. Degree focuses on how many neighbors do you have. Betweenness focuses, for example, if you are placed in a location that you are very important for all the rest of the nodes traveling through you to get to the other places. So you start seeing that 11 becomes an important node because now it's presented in two of the plots. In this one, closeness is how this node is close to the rest of the nodes in the rest of the graph. Or eigenvector could be something like explaining in less plain words how important you are because you are connected to other important nodes. So we do these ranking-based approaches, and then we go and observe which type of users we have in these colors. And let's focus on user type class 4. Let's imagine this is a specific community with a specific attribute. When we go and check their 4 nodes, we see that there's a lot of dispersion. Depending on what we prioritize, we will end with a different decision. Okay, this is good, but we have to go further. We know that we are not considering yet the vulnerability of the system. So how we can introduce that? In network science, typically you can start investigating what happens when the edges or the nodes, both, can have a failure probability. So The inverse of the failure probability would be the edge reliability, and we can start eliminating nodes and getting an information on what happens at the system level with the connectivity. For example, if you start tracking the largest size of the size of the largest component, you will start understanding at which point there is a phase transition from not connected to fully connected network. So with that type of information, you can also even go further. For example, we can start investigating connectivity loss, which is the average decrease in connectivity between, let's say, source and target nodes, or the relative efficiency, very useful in our community to understanding what is the change in the efficiency when you eliminate some nodes in communicating all of the nodes in your system. So I'm showing you here one way of doing it, and look that you only need to eliminate some nodes with certain information from the reliability of the edges. But let's go closer to our community. You may be missing something. You say, okay, what happens with the hazard? Where is the hazard? What happens with the deterioration model that is spread across the community? So definitely we have this pipeline, stressor models, the network level assessment, damage models. You will have, for example, fragility functions that you could even start thinking, okay, what is the level of fidelity that I have to represent the failure probability of each individual component? Well, we presented something here based on traditional and surrogate-based approaches. I invite you to read on when it matters and specifically for which type of decisions you are focusing on. But at the end, you start combining all of this and you obtain what you see on the right-hand side, which is the estimated damage for a single scenario at a specific time, because we have to keep track of the deterioration. But for the people that works, let's say with buildings or with other type of system, and when we don't consider the interaction, specifically the interaction, we may start going from that point to losses, to downtime estimation, but in networks it's different. You have to stop there and say, okay, for this distribution of probable damages, how likely it is that my system behaves. So for a system, for a network, you may have network states. What does it mean is what combination of fail and no fail elements will you have? And this is a very computational expensive problem. For example, for a bridge network of 130 bridges, this is the number that you will observe of possible combination, which is, and only considering failing and not failing. Imagine if you want to consider more damage states. So this will exploit any system. So you note, of course, all failing is very unlikely, all safe, very unlikely. You will have some intermediate states, so maybe you will have to rely on Monte Carlo simulations. But let's imagine that you solve that problem. There are analytical solutions for small networks. Don't forget, it increases very fast with the number of nodes, and you can then rely for larger systems with Monte Carlo. For each simulation, you will have to start sending a lot of random seeds to estimate the recovery time for each element. And then you need a way to create a recovery scheduling, which system you're going to prioritize, how you're going to do this. In the end, you start merging a lot of uncertainty, and you will have different recovery paths. So on the right-hand side, you see one visualization of one recovery path, and we presented a webinar recently, like 2 years ago, that I invite you to see if you want more information. So if you have now a recovery trajectory, then you can start measuring any global metric of functionality. For example, I mentioned already network efficiency, relative network efficiency, which is how much your efficiency changed when the system was exposed to damage. And you can do that also during the recovery, of course, because you have new elements coming back or returning to their original functionality. Look that this is taking into account the summation, the sum of all the trajectories from one node to the rest of the other nodes. And this is the inverse because you want to consider that it is more efficient, it has a lower cost, right? Cost could be measured in terms of the distance. So I am keeping track of the real distance of these links, or even the time, or even other type of metrics that are related with this. But computing this means that for each time step, I have to find the paths from one node to the rest of the nodes, which is a quadratic, almost quadratic problem. For 500 nodes, you are measuring every time step 250,000 possible paths. And that is just for one single line. And you will have something like this. And of course, the webinar was about using HPC with TAC and design safe. Now that we are here in this NHERI community, I invite you to go and check that webinar. So I'm just highlighting the expensive problem that this is showing us. And at the end, we have this plot, and then we go back to our original problem that was linking this with social impacts. So nice, this is a good plot. We have an insight about the infrastructure failures and response, but who is bearing the loss of connectivity when we now use this risk-based assessment? Who is paying the cost or increased cost of now navigating the network, or who is having to wait more time during the recovery? So those type of questions brought us to the second topic that was part of my last portion of my PhD, and is how we can do this together in a single step in such a way that we represent socio-physical system and we keep track of the impacts on each type of user. So let's go back to the original representation of the network. We have V and E, the set of nodes and edges. Now we want to consider some set of users. Users are represented in this case with some color, one of the attributes, but users can have many different attributes. In this case, we have attribute one will represent a social class. It could be socioeconomic class. The attribute two could represent age. And if you want to start combining these two, our proposed approach was, okay, first thing is let's do what we do usually is like we say that by proximity, these users will rely on the functionality of the closest node. That is the first step. But then how can I keep track? And this is my goal, to preserve their information and their impact. So we propose extended the traditional representation to an attributed network approach, which now includes KV and KE, which are matrices that are the node and age weighted set of attributes. For each node, I will have something like this. For example, KV for node V will have a vector of attributes of the weights of attributes one. It means how many people will represent each of the characteristics of attribute one and how many people will represent attributes of characteristic two. If you click in one, even though I'm representing them here with some colors and some size, depending on the total amount of population, they don't have to be just one category. I am keeping track of the full distribution. So I have the distribution of the two attributes. So this benefited us to go further and say, okay, now we can translate the original metrics that were network only metrics to attributed aware ones. So what we did, we went to connect to the connectivity loss was a metric that was used or proposed almost 22 years ago for power networks. So what you hear, I won't go into the details because you have the paper there, but the connectivity loss, again, is the average in the decrease on the connectivity between distribution and target nodes. That was for power networks. So you have regeneration, which are the sources, and distribution nodes. But we want to do this for origin destination. It means any node could be a source node, and any node could be a target node. So this area. There's okay. Thank you, Mohammed. So once you do this, we translated that metric to the particular case where all the nodes could be sources, all the nodes could be targets, and we translated that further. And we say, now we have this attributed network, we can keep track of the nodes. Let's use that information and place it there. So these are the two metrics that we propose in ICOSAR, which was for the minimum, let's use the size of the nodes. It means the total number of the population that relies on that physical node. So this is the same. Let's say this is the extended version of that when you consider the population, and this will give you a scalar, same like this one, and a scalar value for a specific damage state of the network. But the beauty of this was that now we could even keep track of the attributes and keep back and go back and say, why not keeping this in a vectorized approach? So when you observe these weird functions, for those that haven't seen them, is element-wise division, element-wise multiplication, and this will be, let's say, an equivalent representation, but CL in this case is a vector. So you will preserve the information of the attributes and the impact on them. Similarly, with network efficiency, we had this in almost 25 years ago from Latora and Machiori, and then we translated that to the attributed case by keeping track of the weights of the nodes. In the first case, this is the original one extended to an attributed case, but the relative one will give you an scalar, which means how efficient in terms of the number of nodes with weighted. And also you could have the vectorized approach where the efficiency lost by each community will be represented in this equation. A brief example that I will present in one of the conferences that Parisa showed in the National Conference on Network Engineering. Let's imagine that you have this network, original on the left-hand side and damaged after a hazard event occurs. you can do the relative network efficiency and estimate 0.47, which means you lost about 53% of your original efficiency. But what we're proposing today is going back and checking who is using those nodes and what are the attributes of those populations. If you do that, then we could see that by just adding the weights, let's say the total number of people on each node, the new loss on connectivity was smaller, 0.51. So you have, I mean, the loss is smaller. But if you go and check the attributes, this means that the population in color red is bearing larger losses compared to the blue and green one. And this is something very important because now we can send, let's say, we can better inform decision makers. So take into account a more equitable decision-making process. If we present this in a larger example, we have six possible attributes. We have an infrastructure system as the one that I'm presenting here. If you rely on one of the original methods that I showed you, for example, edge betweenness, this will show you which are the most interesting or important elements just by in considering the topology of the network. But this was not our intended approach. Remember that we said attributed will send the population to the closest node. So this is the representation. You will see it's larger nodes when you have more people around that node. And these are the network efficiency and attributed connectivity loss, now considering the vectorized approach. These are the number of nodes that we used for the computation and number of edges. So as we start changing the reliability of the nodes, we start having better efficiency. As we start changing the reliability, higher reliability is lower connectivity loss. In this case, I won't focus on network efficiency because it is not showing much spread. I will explain this in later. But the attributed connectivity loss is showing us that when we go in and cut for a specific edge reliability, each population is very, very different amount of loss. So even almost 20% of difference in the amount of loss. So our metrics are helping us to avoid masking the impact. Instead of having the black line, which was the only thing that I would be able to do using the traditional metrics, now I can go and check who and why is losing a higher connectivity. So we can start also with, as I mentioned, making a more equitable decision process. So let's evaluate the influence of model fidelity now that we have this new representation and why I want to estimate this in terms of the model fidelity. Because as I mentioned, this is a quadratic problem. When I want to estimate the number of paths, I have to rely on the number of nodes that exist in my model. So if you have a low fidelity model with, let's say, 10% of the nodes of the high fidelity model, clearly will be faster to compute. And you can create these probabilistic models and run a bunch of Monte Carlo simulations. But if you don't have this low fidelity, will be very expensive. So usually you will rely on some approaches that will help you to reduce that fidelity. Let's assume that only by using the user-defined hierarchy, you will have something like the left-hand side. But again, when we did this by only focusing on the physical network, we will see that we may be missing a lot of the information of the impacts on the population with these different colors, and we will create a biased estimate. So the problem before was that we didn't know that, but now that we have this attributed representation, it can help us. So for this example, I have a high fidelity model, a little bit different from the previous one. We have 50,000 users. The red links represent bridges. So before, I was eliminating randomly different elements. Here, we have bridges, which each one will have a fragility function. And there's going to be a point source somewhere like here that will start sending different possible scenarios. The scenarios will consider the spatial distribution random hazard maps that you can do with a ground motion model and an intra-event residual correlation model. In this case, I'm using Atkinson and Burr and Ajaram and Baker. And for the fragilities, I'm using Nielsen and Darbosh log normal distribution fragility functions. So eliminating some nodes to reduce the computational cost, that is a common approach, will give us the intermediate and low fidelity, right? How I selected those edges? By using edge betweenness, that is the metric, the ranking-based metric. So if they exist here, it's because they are very important by using that specific ranking-based approach. So we did this, and we computed the two metrics that I showed before. Before going there, I want to focus on the low fidelity, and there are some notes here because we eliminated a lot of portion of the network. Clearly, they became more important. But that important, as I mentioned here in this box, is artificial, and is a byproduct of reducing clearly the physical system resolution. If we estimate now this network efficiency and connectivity loss, we will see something like this. I mentioned before network efficiency was not changing much in the previous case because we are eliminating at random, but we have to create thousands of simulations of possible random let's eliminated edges. So they don't have a much, let's say, difference between users. But in this case, now we have users located close to different areas where you may have more or less number of bridges. And bridges are the only element that could be damaged in the previous network. Roads, we'll assume that they won't be damaged by earthquakes. They could, right? But we're not assuming that. So let's compare in this case, what are the first observations? In transparent, you'll see here, you can see my mouse, you observe what is the high fidelity value. So the magnitude clearly is very different. The number of nodes you reduce from almost 1,000 to almost 250, so it's a quarter, but this is impacting too much the new outcomes. Something that also you observe here with that changes a lot is that now we have the moment magnitude of the earthquake as part of the variable in the x-axis, and you see that there is a plateau. Why this is happening? Because these systems, because not all the edges will fail, so they reach a plateau in the performance, so they don't lose more than a certain portion. But something interesting is when we start comparing what happens with the two metrics and also between the model fidelities. For example, before going to the animation, if we check here, the purple one, it was the, let's say, the lowest network efficiency user attribute, and now it's the highest because I changed the resolution of the network. The green one was somewhere in the middle, now is the poorest. So I am changing the order of the prioritization in something that I don't want. Also, the good thing of having two possible network level metrics is that they can show us different information. For example, the connectivity loss of the purple one is very small. It means that they are almost always connected, even you lose the functionality of the bridges. But they're the population with the highest loss in efficiency. Why? Because even they keep connected during the damaged states, they have to reroute a lot. They have to do, let's say, longer distances, so they lost a lot of efficiency. And they're showing those two things. But if we change again the same problem, we change the fidelity, we may start seeing a lot of variation with the original or the expected original social vulnerability. So we are observing with this that we are hindering decision making for some people by reducing model fidelity. I don't think that is a good conclusion to say we are hindering or affecting this. A good conclusion could be also trying to do something about it. So what could we do to reduce the computational cost, but keeping track and without affecting much of this order or these social inputs? So in ICOSAT, let's go back to this origin destination network. We propose a method based on socio-physical communities that we'll explain in a minute. Similar to what I did before, I have the high resolution model. We have two intermediate and low resolution models defined with the edge betweenness metric, which is very important for our community. And we, of course, we put the networks, the attributed networks, the users into each of the nodes, and we went to select now these social-physical communities. Finding social-physical communities means trying to find what are the communities of nodes that are densely connected together, but also are, let's say, they don't have much connectivity to other communities. So this is a common algorithm or set of algorithms in network science. And if you use the information from the network alone of the topology, for our example here, you have something like this. Clearly, these are densely connected, so they are one community, less connected to others. Definitely, until you start doing this, finding in this case three communities, right? This is as an example based on modularity maximization. But again, in this case, we would we would miss the opportunity to include the information from the users. That was all the thing that we wanted to include. So if we use the information from the users, that they are spread across the community, across the infrastructure, we could use another set of community detection algorithms now for attributed networks and finding new communities that we call socio-physical communities. Why socio-physical? Because now you're balancing two type of information. One is the information of the user attributes, and the other one is the topology or the physical structure of the network. We are finding some hidden relationships or complex interactions. And our proposed approach to reduce the computational cost is to select or pick some of these nodes that are within each of the communities. So we want, now that we know that these communities are important because they share social and physical attributes, now we can start selecting a certain portion. This is a heuristic approach. Let's select a number of nodes within each community. This is a ceiling function. You see the ceiling function, meaning that I won't eliminate any community. If the community is a single node, the minimum number of nodes will be one. So we obtain this type of approach. Let me show you a more realistic example. There is one method called, there are many, but this one is called Louvain Extended Vertex to Vertex Attributes EVA algorithm, and optimizes the modularity, which is a physical metric, and the purity, which is in this case is an attributed based metric for the partitions. So Z is going to be a score that balance out this purity and this modularity, and what you will have to find is which is the alpha that maximizes the Z. By doing that, you can have a new set of communities. For example, here I don't remember, it was 30 or 50 communities. And for each community, we pick different levels of fractions of nodes. Let's say gamma equals to 20 and gamma equals to 0.001 to select the minimum. So these are representative nodes that will, I would say, parentheses, semicolon, sorry, they will represent these communities, and we will eliminate, but we won't eliminate the nodes, we will eliminate their relevance. We won't consider them when we're going to compute the network level estimate, but we're going to keep them for analyzing the connectivity. Why I went in this direction? Because if all what we do by eliminating nodes is because we want to reduce the number of paths to estimate, clearly here I am eliminating the number of computations of that I will present. I will show you in a second. But I am not eliminating the real connectivity that the socio-physical communities have. So let's go and see what we have. So we have the high resolution, we have the intermediate and low resolution, and we have three possible fractions, 20%, 10%, and 0.1% of nodes selected per socio-physical community. Let's, for each one, estimate by eliminating randomly the edges of the system. Let's evaluate the network efficiency and the connectivity loss. Before going there, because I want to make a fair and fast comparison, I want a fast convergency of these type of estimates. I will create, let's say, a comparison module where I have a synchronization of the component failing. Why? Because they have different number of elements in this type of reduction of fidelity. So I will keep track of which elements I am eliminating the high resolution, and if they exist in these other two, I will eliminate them too. Of course, in these three, when they are eliminated here, they are eliminated there. So by that, I am making something that's called correlated sampling. So these are the results. High resolution, this was the plot that I showed before. Now we have a parenthesis. This is the number of nodes, and these are the number of nodes used for the computation of the network efficiency. Because I didn't reduce anything, you see the same number. So there is a low impact in network efficiency, but I want to say and mention that the network efficiency is a metric that any small change means a lot in terms of the efficiency, because this is a global metric, no? Don't forget that it's already averaged. What happens when we reduce the fidelity by using only the network information? Well, we are clearly impacting because we are creating large gaps between the original, you see in a transparent in the background of these figures, the original value and the new value, and it can change because before In the intermediate one, I changed from almost 1,000 to 330 nodes, and the lowest resolution, almost 200 nodes. And you observe how this is changing the value. We don't know much if the dispersion is higher between the communities, but at least we know that the value is changing a lot. Now, what happens with our socio-physical communities? You see, we are having a very good result in this case by using only 215 nodes, similar to the lowest resolution. What is the difference? As I mentioned before, I didn't eliminate the edges. Here I have 200 edges, and here I have the 1300 edges, original number of edges. So what we are doing is we keep the same fidelity, but we reduce the computational cost, now reducing the number of nodes. This is quadratic. Don't forget, by eliminating almost 700 or 800 nodes to the square, we are reducing a lot the number of paths. Definitely, the paths computed in this and the low resolution model will be computed faster because you have less possible paths than in the other on the right hand side. But 800 is 50% of the number of nodes eliminated. Sorry, 800 is almost 80% in this case of the number of nodes reduced. You can go further and eliminate and keep track only of 10% or just almost one. But at this point, we start seeing larger differences. Clearly, gamma is a parameter that you will have also to find. But as I mentioned, you could make this as a way to first try to track how much you could eliminate without affecting the population. And then when you have something like this that you are, let's say, you have a reliable estimation, you can go and run your probabilistic approaches. Let's check the connectivity loss, which was most important, most interesting for this case. Again, if we keep track of the high resolution result we observed before, if we keep track for the green user attributes, we have something like a very small connectivity loss when we have around 0.9 edge reliability. By changing the resolution, we change this a lot. We created probably more conservative values, but still we start changing who is bearing larger losses. The yellow one definitely is always sharing larger losses, but then we have somewhere here some purple colors, and now we have some blues and some greens. So these will affect in the future our decision making because we will prioritize differently if we use this type of metrics. With our approach, we have a better simulation of those impacts, smaller errors or biases. So we have to understand that, yes, if we reduce too much in this approach, it will affect, but there is somewhere between 10%, 20% in this specific example that will work. I will start closing this presentation because I'm getting closer to the 35 minutes. So I want to say in this one that the proposed formulation not only avoid masking the impact that we already observed before, but we are also improving computational efficiency without affecting those estimates. So the key takeaways of these presentations are, first, now we have a way of representing jointly the socio-physical systems that will have an application uh, first by enable us to estimate disaggregated impacts and explore hidden relationships in these socio-physical communities, for example, for designing interventions. Second, we avoid masking the impact of service disruption. So the decision making becomes more transparent, and now you can consider whether those specific social characteristics or user or sectors or economic characteristics can have different capabilities, for example, for recovery. Third is that the model fidelity can hinder decision making. So it calls us like to find or to propose objective ways to select this type of fidelity. And our method can help as a way of testing where your abstraction will lead to biased estimates. And this can go further, and I'm exploring during my postdoc, and something I present in EMI, is if we can now, that we have this representation of the social physical system, include the dynamics of the population moving that will change the demands of the system, but also will change the relevance of the nodes around the system, and start observing, for example, when it matters to have, for example, adaptive decision making that can help us to manage dynamic infrastructure systems. With that, I would like to thank my collaborators and my advisor, Jamie Allen Paget, funding agencies, of course, you, the GSC, for inviting me today. I'm very happy to be here and happy to take any question. And we'll leave the room with this final sentence, which is that I think that our community, in specific this community, should seek for urban systems that are safe and resilient clearly, but also we have to keep in our minds that as engineers, as modelers, our approaches should not bias the results or the decision making, and we can have sustainable future generations. And thank you for your attention.
Okay. Thank you so much, Dr. Rincon. You're one of the person who work on the cutting edge AI and also inclusion of them into the resilience. So I am sure that all the people who are here now have a clear understanding of your work. I will open the floor for questions. Feel free to raise your hand or put your question in a chat or just open your mic and ask your question.
Don't be shy.
Yeah, don't be shy. I can start. Usually it is like that. We say, ask your question, then I start, and then other people ask. Okay, I will ask the first question, especially at the end of your presentation. During your postdoc, you are focusing on the dynamic graphs, and I'm gonna touch on that. And I want to ask a general question: how much you think these approach can be adapted to other regions? I'm going to touch the generalizability of these approaches, so we can have a unified framework that use this information and can be applied to any region that we are looking for that.
Thank you, Parisa. The generalizability, I think it's very important, and it was part of the goal. As you see, it is a framework that I'm presenting from a network science perspective. You
Yeah,
just need attributes, and attributes could be anything. If you think in your social systems, it could be any characteristics that in the future you expect to bring, for example, social communities that are also part of NHERI and say, hey, come here, let's see what happens when you have this attribute, this impacts on the networks. And don't forget that impacts can be anything, could be any hazard, could be any infrastructure, failing connectivity. And I am just showing what you could do at the connectivity-based approach. But you could even go further, and now that you have the users, you could even also make flow-based analysis where you consider where they in reality want to go or need to go. So I presented this in a very generalizable way because that was the purpose. It's like you can expand this wherever you want to go, at least from our perspective, what we are observing. And the dynamics can be also included, for example, during recovery. There is people that will leave the area, there's people that will return, that will definitely affect dynamics of demand and availability. There are many things that you could do. And what we wanted to do is something that help you to track the global impact. Even your users are spread, because don't forget that I don't use clusters. The
yeah,
clusters that I use was just to reduce the number of nodes, but my populations with similar attributes will let's say will be represented by a single global estimate. Now going a little bit further and giving a little bit more of information, users can be, and attributes could be anything. For example, sectors. If you have commercial, industrial, educational sectors that they want to connect to, you want to know that those are also attributes. So social is not only, let's say, people with their social characteristics, it could be anything. And that was something that we tried to create in this framework.
yeah. I think I agree with you, and I have a same thing of direction. And my always only concern is about because you said that if you have the attribute, you can do whatever you want. And my only concern always is on the data availability. And I think now a lot of people are trying to boost on that side. Okay, thank you. Any other questions? Use this opportunity because later finding Dr. Rincon is difficult. So I encourage you to
My
ask
email
your
is
question.
there.
Yeah, sure.
My
I
email
am
is there,
trying
but it
to.
would be nice to answer the question here.
Okay. I will wait a couple of minutes and then I will move forward.
So maybe I can say something else now that you mentioned availability of data. Let's focus on the minimum data is the attribute. I
Yeah,
said educational, the sector. If you are commercial, that is the minimum. You have
yeah,
information about the impacts on commercial and educational. Or if you have the census tracts, you have a minimum layer of information, right?
yeah,
You know the certain level of attributes. You don't need exactly the realistic value of the specific dot, but you know and you have a sense and you can have, because you have the special distribution of those attributes, you can start doing nice evaluations.
Yeah, yeah, yeah. I agree on that. Um, okay. Um, Dr. Rincon have give us the permission to put his email here. So if you have any questions, you can reach out to him for any further question. I want to thank you because I know that you were in the trip and I know how much it was difficult to handle everything. I appreciate it a lot for giving your time to us. I think by this, we are gonna give our applause to Dr. Rincon and we will move forward to the next part. Thank you so much.
Thank you so much, everyone. All the best.
Safe travels.
Yeah. Okay, I'm gonna move forward. Presentation mode. What? Decided to start from the first page, apparently. Okay, we review our agenda today. Okay. In couple of minutes, something like 5 minutes, we are going to have our NHERI GSC research subcommittee meeting. We are gonna have two group of breakout rooms that Robin will open them, and then you can join. Okay, one of them is main room, the other one is the breakout room, and you can join if you have any interest either for the coastal or the geotechnical. For the coastal subcommittee, today presentation is by Dr. If I am pronouncing it incorrectly, I apologize for that. Dr. Dylan Sanderson, and he's going to present on community resilience modeling for high tide flooding amplified by sea level rise. For the coastal people, I would say that that's a hot topic, and I would recommend to join for that. And I want to thank Sadek for arranging all the things. For the geotechnical subcommittee, you should go to our breakout room. And today's presentation is going to be by Dr. Siamak Yousefi, and he's going to present on the geotechnical behavior of vegetated soil in coastal wetland. Another interesting topic, and I recommend to geotechnical folks. And I want to thank Mohammed for arranging this presentation. Moving forward, I want to say that our next general meeting is going to be held on 17 April, and Nicole is going to present. We will provide you with the further information later. That is going to be also another good topic. And by this, I want to thank U.S. National Science Foundation for funding us and providing this opportunity that we can have these meetings and these presenter. For time being, because we have about 5 minutes, we give a 5 minutes of break, and later we will see you all in our RSR meetings. Perfect. Okay.
All right. So I'm going to go ahead and open the breakout room.
Yeah.
And if you were interested in the geotechnical speaker who was in room one, Simak Yousefi, I hope I pronounced your name right. Please correct me. I know.
Hi.
Yes, you're going to be in breakout room one, and I've opened that room so y'all can go ahead and start moving in that direction. If you have any technical difficulties, let me know. I'm here to help.
Great. Thank you so much.
Thank you.
And I'm not a doctor. I'm a GS student, by the way.
Yes.
The future
And
doctor.
And then Dr.
yeah.
Sanderson will be in the main room
Yeah.
with Sadek. Yes.
Yeah.
Welcome to both of you.
Yep. Robin, I think because
Thank
all
you.
people are here, we may want to start. So I would leave it to the Sadef and the
How should
other
I go to
breakout room.
your?
Yeah, we can start and go for that.
I think you're
All
right.
right.
Yeah.
Thank you, Parisa. Thank you, Robin. Maybe we should give it like another minute for the people that just left to come back and then we can start.
Does anyone need help going into the other breakout room? If so, just let me know. Sometimes people get
I
stuck.
think I have. I've
Okay.
never done that before.
Okay, so I'm finding your name on our list and I will help you move, but where are you? There you are. Okay, assign to, okay, it should pop up on your screen now and ask you if you wanted to move.
Also, I do have.
You as well, Shova?
Yes.
Okay, I'm looking, there you are. Assign to geotechnical. Okay, it should pop up and you should be able to move now. If anyone else would like me to help them move, just put it in chat so we don't interrupt the main room. But we're excited. Thank you so much, Dr. Sanderson. And you should be able to share so whenever you're ready.
Okay. Do we want to wait a few minutes till 10 or should I just go ahead and get started?
I personally would go ahead and get started, but it's up to you.
Okay.
By the time I would try your screen and make sure it works, and then by the time we do that, it'll be a minute to noon.
Okay. Yeah, sounds good. And
Perfect.
Sadeg, are you kicking off
Yes.
the Okay, cool.
I
Sounds good.
see here the screen. We can see it. So I would just go forward and start the introduction. So thank you so much, everyone, for coming to this meeting today. And it's my pleasure to welcome you all to the Coastal RSR meeting. And we are very happy to have Dr. Dylan Sanderson with us. Dr. Dylan Sanderson is an associate research scientist at Johns Hopkins University and a PREP associate at the National Institute of Standards and Technology. His areas of expertise include both coastal engineering and community resiliency modeling. Prior to beginning his current role, Dylan was a National Research Council postdoc fellow at NIST. Dylan obtained both his PhD and Master Science degrees in civil engineering from Oregon State University. Dr. Sanderson also previously worked for U.S. Army Corps of Engineering in the Coastal and Hydraulics Lab. Today, he will be presenting a talk titled Community Resiliency Modeling for High Tide Flooding Amplified by Sea Level Rise. With that being said, please join me in welcoming Dr. Sanderson. Thank you.
Cool. Thanks for the intro. Yeah, so as was mentioned, the title of my talk is Community Resilience Modeling for High Tide Flooding Amplified by Sea Level Rise. And this was some work that I did during my postdoc that was funded through the National Academies of Science, Engineering, and Medicine. So I sat at NIST, which is outside of DC. And for this part of the talk, I worked with two people in the community resilience group at NIST, Terry McAllister and Jen Hegelson. As I wrapped up this work, I guess about a year ago now, so March 2025. And when putting together this presentation, I'm really excited about my current research as well. So I kind of have like a subtitle to this talk, or like kind of a footnote on this talk. I'm actually going to present on some of my current work towards the end, which is some hurricane work I've been doing. And so this I'm working with my collaborator Don Slynn, who's also at NIST. But I'll touch on that towards the end. So community resilience, often defined as the ability of communities to prepare for anticipated hazards, adapt to changing conditions, and then withstand and recover rapidly from disruptions. A lot of times this is shown graphically with this kind of like resilience curve or swoosh. And the idea here is that on the x-axis, you have time. The y-axis is, I put functionality as some kind of metric you can track. So for example, it could be number of people with electricity, like in your community or in your city. And the idea with resilience is you're tracking through time, some natural hazard occurs, you get a loss in that functionality, and then there's some time to recover. So for example, you have everybody in your community has electricity, natural hazard, people lose electricity, and then slowly as the infrastructure is rebuilt, you're back to the pre-disturbance conditions. If you kind of look at the definition of community resilience, this curve here is largely focused on this last bullet point. So the build
And some of the results and conclusions we had so far on this research. Coastal wetlands are the intermittently to permanently flooded tidal zones located between the dry terrestrial systems and the deep water aquatic systems. They can be classified based on their distance from the ocean, their geological properties, their chemical properties, and their biological properties. Coastal subsidence and inundation due to extreme events such as hurricane and storm surges. So understanding these will help us better make decisions in future. So in the following slides, I will talk about the role of these environment as a natural buffers, the threats that are putting them in danger, and also the stability factors that need to be understood in order to be able to predict their behaviors under such extreme events. Well, coastal wetlands, beside the fact that they provide essential habitat, food, and breeding grounds for different species, they play as an essential role as buffers. They reduce the wave energy, they limit the shoreline erosion, and they provide protection during storms and hurricanes. And they also provide mechanical support and the open water.
as a test bed. Really focused on using Galveston as a test bed. So Texas, shown here in gray. The location of Galveston is kind of more on the northeastern part of the coast, a couple hours away from the Louisiana border. And you can see the background here shows the Galveston Island. So one thing to note, it's a barrier island, so off the mainland of Texas. And then for the data we used, we had buildings. So that's all of the black points that are shown here. Each black point's a building. We also had the road and bridge network. So that's shown up here in the top right corner with these line segments. And then we also considered electric substations. It may be a little hard to see with my laser pointer, but it's these red dots throughout the island. So for this work, we considered buildings, electricity, and transportation. And we used Galveston because there's been a lot of work with Galveston for resilience modeling. I'm not sure if Raul talked on this, but I know they've done a lot of work at Rice collecting this data and putting it together. So it's available in NHERI, which is a community resilience modeling environment. And so my postdoc at NIST, I kind of broke it up into two different pieces. One was this just assessing the impact of sea level rise. So that's the first part of this talk. And I have the citation reference down here for the work we published on this, if anyone's interested in diving into the details. But for this work, was really interested in using as much publicly available data as possible, particularly to assess the impacts of sea level rise. And so what we did was we took future projections of sea level rise at Galveston, overlaid that on top of future projections in the tidal signal. So tides are very predictable. And so we just considered, we had this future record of water levels that span from 2025 out to 2100. And this is one example of that shown in the top here. And one thing to note, we didn't consider storm surge or anything, so it's very deterministic relative to the irregular occurrences of hurricanes. And then we would use this time series, and then every single day go through and track, okay, so what's the highest water level for that day? If, for example, in 2030, about February of 2030, we're at 1.2 feet, we then go down and use the closest inundation layer we had. This is also some public data that NOAA has on their Digital Coast website. So we use the 1 foot inundation layer and then track how the impacts to the community. So how many buildings are exposed to flooding, how many roads are flooded, consider increases in travel time, and how many buildings lose electricity. We could then fast forward that. So we do this every day. So this is another example looking in November of 2080, about 3.9 feet of sea level rise. We then go to the 4-foot inundation layer, and you can see there's a bit more flooding on Galveston Island. And so we'd repeat this, like I said, every single day in our title record. And then we can look at the results in different ways. So this is an example of looking at the building exposure. So this is under the intermediate sea level rise scenario in the year 2100. And looking at the number of days in 2100 that every building is exposed to flooding. So in this case, yellow means the building's flooded the entire year, whereas purple means it's flooded one day per year. So kind of have that gradient. So yeah, the islands for the intermediate sea level rise scenario, and then this red inset box here is the panels A, B, and C for the low, intermediate, and high sea level rise scenarios. And so you can start to see at each building, the potential exposure that that building will be subject to. One thing I like to note about this figure is that you'll see that kind of on the bay side of the island, the buildings are a lot more exposed to flooding compared to on the shoreward side. It's really relevant kind of on the more western end of the island. This section here where my laser is. This is because Galveston's really exposed to back bay flooding. So you get a lot of flooding that comes in from the bay side, whereas the front of the island's more built up with dunes, and they have a seawall on the eastern end of the island. So this is something we repeatedly saw in a lot of our analysis, just the exposure to bayside flooding. We can also really dive in and look at a single building and how a single building may be exposed to sea level rise. So this is looking at this building up here with the red dot, kind of on the more western end of the island. We have, again, the low sea level rise, intermediate sea level rise, and high sea level rise scenario. And these plots show on the x-axis time in the year, and the y-axis is number of days exposed per year. And so you can kind of see across time the increase in exposure. So for example, just focusing on the low sea level rise scenario, I like to really point out that there's a lot of uncertainty even within these sea level rise scenarios. So for example, if you just look at 2050, the median's about 200 days per year exposed. This bottom confidence interval was a 17% confidence interval, and that's about 100 days per year exposed. And then on the high end, maybe about 300 days per year exposed. So that range, the 100 to 300, there's a lot of uncertainty even within just the low scenario. Another thing we did with this work was the orange, purple, and I guess dark purple or black lines here are at the building. But we also looked at the census block level. So really trying to compare and contrast, like, okay, what if you just at the building scale versus the census block level? So the gray line here is the census block centroid that this building is located in. And you can see just how different the results are, where, for example, this building may be exposed 90 days per year in about 2040 if you look at the building level, but at the census block level, it's 2075. And that's a huge difference. So just really emphasizing, in this case for flooding, the importance of doing this work at the individual building level. I also show down here just another example. This is a building that's back here more on the northeastern part of the island, but in this case, the census block is exposed a lot sooner than the building itself. I don't show the results in this presentation, but we also can do the same thing with number of days per year without electricity, or number of days per year with increases in travel time from every building to different points of the island. So we did the exits to get off the island as well as the hospital. So I did that for the first part, kind of the first half of my postdoc. The second year, changed gears and focused more on agent-based modeling. One of the things that's really exciting to me kind of about the community resilience modeling world is that they're very holistically consider impacts to to like there's the natural hazard, the natural environment, the built environment, and then the social environment. And so they like in the community resilience modeling world, it's often consider all three of these. And one way to do this is through agent-based modeling. So if you're not familiar, agent-based modeling is a type of modeling framework where you have a bunch of agents in a model. You have some environment that you put the agents in. And these agents, each agent perceives both the space that they occupy, so their environment, as well as other agents. So for example, maybe this agent can see this agent and this agent, and like what's happening in their environment. And then each agent also has rules associated with them. So for example, if you have this agent right here and they see this agent, and they observe this agent take some action, then maybe there's some rule that this agent has. It's like, okay, and I'm going to take this action. And if this agent sees that, then now they take an action. And this process repeats in this modeling framework. So that's just kind of like traditional ABM or agent-based modeling approach. For my postdoc, I got really kind of fixated or really interested in this paper from Allison Heppenstall in 2021. It's this future developments in geographical agent-based models. And they talk about this idea where what if instead of having these like rules, we have more intelligent agents where we essentially let these agents learn for themselves how to respond to their environment. They capture this, I think, pretty well with this sentence where they talk about how these spatial learning agents may both better reflect the actual behaviors of humans and model their behavior under changing conditions. And so for this work was really interested in, okay, thinking about like sea level rise and climate change. Can we have agents that represent households and essentially learn how to respond to these impacts from sea level rise, and maybe like figure out kind of, or have an idea of how people may respond to sea level rise and try to use that as a decision support tool. So for this learning piece, use reinforcement learning. In the ABM world and reinforcement learning world, they use very similar terminology, so hopefully don't get too confusing here. But the idea behind reinforcement learning is you have an agent. The agent also perceives its environment. You tell the agent, like, you want to maximize some reward. So in this case, in this paper, they try to teach an agent how to play Atari, where they're maximizing the score. And then all you tell the agent is like, here's your actions. You can either move left and right. You don't tell the agent how to play Atari. It's just, you're trying to maximize your score. And then through these algorithms, the agents learn basically how to play Atari themselves. So for example, they learn like, okay, if I'm here, I need to like move right or move left, etc. Yeah, so I wanted to take this approach, take the reinforcement learning concept, apply it to this agent-based model where we have these agents that essentially learn for themselves how to respond to the impacts of sea level rise. So at a big picture, up here at the top, these agents perceive their environment, and then they take some action based on what they perceive. Diving into a little bit more detail over here on the left, we set up these agents so that they perceive 8 different inputs. So they're looking at how many of my neighbors have left, how often am I exposed to sea level rise, how often do I not have electricity, and then how often is there an increase in travel time from my house to somewhere else in the island. So that's this first group of 4. We also let the agents know basically like information about the building they occupy. So for example, they observe like, is my building already elevated? Which case we assume their building's no longer impacted from flooding. Or do they have an electric generator installed? So trying to simulate, okay, they're not going to be impacted from power outages, but then they still have electricity. They're aware of their current building. And then they're also aware of cost. So they're aware of how much it costs to elevate their home or how much it costs to install electric backup. And so we have all of our agents in our model. They perceive these inputs, and then they learn what action to take. So in this case, they can either take no action, so they do nothing. They decide to leave, so that's simulating migration. They can elevate, so building on ground, elevating their structure, or install electric backup. Yeah, so the idea is, as agents learn how, based on these inputs, what action to take. Within like reinforcement learning, the other kind of important piece is the reward function. So that's shown here. And I like this, taking this idea of reinforcement learning and putting it into the ABM, because I think the reward function is very easy to understand, and thinking about like community engagement. Hopefully people can understand like, okay, this makes sense what these agents are trying to do. But the reward function here, it's a simple summation of 5 terms. The first one is this place reward. So this is essentially like thinking about like place attachment, people being attached to their home. It's kind of hard to like tell someone, oh, you should just leave. So the first one is place attachment. The next 4 terms are penalty terms. So essentially like how adverse these agents are to different penalties. So the first one would be a penalty if you live in an empty neighborhood. And then the last 3 here are the building, electricity, and transportation. And one thing to note about this reward function is that it's the agents are trying, it's kind of like a little bit nuanced, but the agents are trying to maximize this, like not just at their current step, but they plan ahead for future steps as well. So they start to observe like, okay, maybe I don't get the maximum reward at this current step, but maybe it'll pay off later in sequential steps if I take this particular action. So these agents they plan ahead for future steps. For this work, we set up 8 different agent types. So agent 1 to agent 8. Agent 1 we called the baseline agent, whereas the other agents varied by that from one I guess condition. So agent 2, for example, is more near-term focused. So they don't plan as far ahead. They can't quite see the benefit of taking their actions. They're more short-term focused. Agent 3 is the opposite, where they're more long-term focused. They essentially can plan more steps ahead. Agent 4 is more attached to their home. And then agents 5, 6, 7, and 8 are just more adverse to these different penalties. So the neighbor, building, electricity, and transportation. This plot shows what if we took the same agent type, put it in every building, and then run the model. So the first one would be if every building or every agent in our model is agent 1. These are the results. So the color bar is down here on the bottom. And you can see you get a mix of agents that decide to leave and agents that decide to elevate. Agent 2, on the other hand, that's the more short-term focused agent, can't plan as far ahead, and they all decide to leave. They basically can't see the benefit of if I elevate my home or install an electric generator. They see their impacts of sea level rise and they decide to leave. And then agent 4 down here is the one that has a higher place attachment. So they're essentially like, I'll do whatever it takes to stay in my current home. So you see a lot more elevating, as well as some down here that also install electric generators. There's more results to this. I'm not going to go into it too much. If you're interested, there's additional details in this paper here. So now I'm going to kind of pivot gears, just because I'm really excited about my current work, and this is not advertised. But this is more focused on hurricanes. So I'm more in the weeds of this work right now. And the idea behind this is that, so Hurricane Ian made landfall in 2022 as a Category 4 storm off the southwest coast of Florida. It was the 3rd most costliest hurricane in U.S. history, so over $100 billion in damages. And typically when you do like this hurricane modeling, a lot of times these models consider like a bare earth model. You might have these bottom friction coefficients that get turned up or higher through urban environments. But one of the things we're really interested in for this work is, can we model how surge and waves interact with the built environment, particularly at these larger regional scales? So there's like modeling like open foam and stuff that like single building, you have waves hitting it. On the other hand, you have models like AdCirc, which is very large spatial scale. You just turn up the bottom friction coefficient to represent buildings. And in this work, we're trying to figure out this kind of in-between place of where can we actually model buildings and waves interacting. So for this, we're using Estero Island as a test case. So off the coast of Florida down here in the red box, we have Estero Island. Our domain's about 3 kilometers in the cross-shore direction by 11 kilometers in the longshore direction. And for this work, my collaborator, Don Slin, he'll run AdCirc and SWAN at these large spatial scales. And then we extract those AdCirc SWAN points, and then we're running XSpeech on this much smaller domain. So we have our things such as water elevation and then 2D SWAN spectra that we apply for the forcing for XSpeech that we then run on this 3 by 11 kilometer domain. And we're doing this at 2-meter resolutions. So the kind of important piece to this is the buildings and the built environment. We use this building inventory from Mershad Amini et al. So they went down to Estero Island, collected a lot of data. They have information about building footprints, as well as attributes with all these buildings, such as first floor elevation, whether the buildings are elevated, not elevated, foundation type, as well as the observed damage from Hurricane Ian. So we can use that observed damage to validate our model. And in XSpeech, we just represent this as abrupt changes in the ground elevation. I think I actually saw an email last night through NHERI that they're giving a seminar on the collection of this data set. So it is really interesting work. Okay, this is a animation. Hopefully it's coming through all right on y'all's end. But just showing the waves propagating from the offshore. This inset here, you can see we have these green boxes are our buildings, the building inventory. And if you look at like a building, you can really see a lot of wave reflection off that building. Kind of behind the first row of houses, there's a lot of chaotic energy where you have a lot of wave reflection. Off the second row, waves kind of coming around the first row of building. Very chaotic. And if you also look a couple of rows back off the shore, you can see there's not much wave energy. So as you might expect, the first couple of rows of houses dissipate a lot of that wave energy. This plot shows over the domain if we run the model with a bare earth on the top versus with buildings. And you can see throughout, not at the individual buildings, but throughout the domain generally, this is plotting significant wave height. Generally without buildings, you get larger wave heights over land compared to the with buildings case, just because that wave energy is dissipated. And then we can also go through and extract at every individual building different statistics. So this is significant wave height, again, kind of right at the buildings. So the black dots are buildings, gold are this simulation with no buildings. And I just have a line of best fit here. And then the x-axis is the distance to the coastline. So this is looking at maximum significant wave height, the maximum wave height that's observed in that entire record. This horizontal impulse is essentially a cumulative force integrated across time, maximum water level surge plus wave, and then just the maximum water level. And so yeah, one thing we're seeing here is that at the individual buildings, you get a large increase in wave heights that's largely driven by wave reflection. Okay, one thing that I'm also recent progress here that we've made is we're starting to sequentially remove buildings from our model domain. So this simulation, I circle these buildings here that are removed during this animation. But yeah, we're running XSpeech, and then we set a threshold for every building. And once that threshold is exceeded, those buildings get removed. So that essentially allows more wave energy to propagate behind those buildings. And so this process repeats where you get this sequential failure of buildings, allowing wave energy to keep on propagating further overland. And as far as validating this approach, we use that building inventory from Mershad et al. So the top is the observed damage. We say anything that's standing is damage state 0 to 5, destroyed is damage state 6. And then the bottom here are the XSpeech results. And if you look at this at a high level, you can see we're doing pretty well with reproducing the observed damage. As we might expect, on the base side, not as many buildings are destroyed, whereas on the coast side, we're getting more buildings that are destroyed. Can also quantify the accuracy of this. So this is a confusion matrix. The X is the XSpeech results, Y is the observed damage. So this corner up here is number of buildings that X speech predicts are standing, they're actually standing. This one, this 330 down here is number of buildings that X speech predicted are destroyed compared to the actually destroyed. And then the two offsets here are the error. So again, overall, we're about 88.7% accurate. So we're really happy with how this is turning out. This is my last slide. Just wanted to show zoomed in here. On the left is the observed damage. The right is the X speech. This is this region here, but it's really zooming in and showing how well this approach is doing. If you look along like the first row, for example, you can see we have like destroyed, destroyed. These two are standing. We're matching it pretty well. And you can kind of go along the first row and see we're doing pretty good. There are some errors back here, but again, kind of like as far as number of rows of houses back, we're doing pretty well with the reproducing the observed damage. As far as concluding and wrapping up, kind of the two pieces of the talk. The first one, the sea level rise. I think just really emphasizing that building level analysis is important compared to doing things at the census block, particularly for flooding, where there's a lot of changes over small spatial, I guess, resolution. And then for the X beach result, we're showing promise for reproducing observed damage during hurricanes. I have my contact information over here if anyone's interested, as well as for the sea level rise work, some citations, if you are really interested in getting into the weeds of this. And that's all I have.
Very great. Thank you so much, Dylan, for the fantastic presentation and like a lot of like cool things you do together, jumping from sea level rise to here, monitoring the hurricane. So thank you so much. Any questions for the people in the room?
Hopefully not too much material, but
It was great.
cool.
Well, let me start actually with one question here. So I have a question for the last part of the modeling that you used. So I assume the first part, the sea level rise that you modeled, the high tide, you do not have like a wave resolving model. You said you got it from NOAA that we basically add, but here the last part you use the ad circ and so on for like the offshore, then do the X beach with the closer to the shoreline and the run up. So how did you decide with the X beach that which structure is, collapse and which one is not? Like,
Yeah. So like you said, we're running the X beach with the phase resolving model. We run X beach, we're running it for a 7-hour duration. And then we stop the model every 15 minutes. And I have this script that goes through and adds up essentially the cumulative force at every building. So it's the force integrated with respect to time. And then at every building, we also have a threshold. So buildings that were built after 1974, there were basically building codes that were implemented in 1974. So those thresholds are a little bit higher.
oh, I
Buildings
see.
before 1974 are lower. And then we sweep through and check, okay, has this building exceeded that threshold? If yes, then we remove it from the domain. And then we keep the X speech running after that.
Okay, cool. So you get the wave forcing on the structure and just check it with the like the whatever the code they had. If it's more, we assume it's failed, and then we
Mhm.
remove that and we continue.
Yep.
Interesting.
Yeah.
Very cool. Any other questions in the room? I assume it's not. Well, thank you again, Dylan, for accepting our invitation for this talk. I really enjoyed because it's kind of like related to what we do in Delaware. Thank you so much for coming, and I really appreciated your time and effort and preparing this. And thank you so much, and best of luck. Appreciate it,
Yeah, of course. Thanks for having me.
of course.
Is there more about this the NHERI group, or that's it for the day?
I think that's it for the day, Robin, right?
Cool.
Like we finished the talks for today, and
Yes, that's it.
Awesome. Cool. Well, thanks for having me.
Of
Thank
course.
you
Thank
so
you.
much.
Have a good one.
All right. See ya.
Bye bye.